Welcome to the Can-Am Roadster Spyder RT Technical Training Series Part 3. Hello, my name is Rich Klein. I'm the coordinator for technical support and technical training. Joining me again today in this webcast is Patrick Eppolite, who is our technical training developer. Patrick has extensive knowledge of the electrical system on the Spyder RT and will be hosting most of this webcast. Missing today is Kurt Otteson, our Spyder specialist, who is actually out riding Spyders today. Patrick, we know we're talking about electrical today in this Series 1 of the electrical section. What exactly are we going to learn today?
Well, first I'd like to say welcome back to everybody for training session number 3. Today what we're going to cover, Rich, is an electrical schematic overview, and then we're going to start to look at some of the individual circuits in depth about their operation.
Okay, that's great, Patrick. But first let's review the training schedule. Back on September 30th, we aired Part 1, which was a vehicle overview in PDI. On October 14th, we viewed Part 2, which was a basic buds operation and basic maintenance video and body panel removal. This is the electrical Part 1 section and builds on the other two webcasts. So if you haven't seen the other two yet, you might want to check those out before moving to this Part 3 series. Also, make sure that before watching Part 4 that you review 1, 2, and 3 as well. Remember that it is mandatory to have completed the Spyder Training Series DVDs 1 through 5 as well as DVD number 7 and also the Part 1 webcast, which was aired on September 30th, in order to receive your fall demo units. After each webcast, go to the BRPTI website and take the short verification exam to receive credit for viewing this webcast. Also remember that completion of this entire series will be mandatory for you to receive Spyder RT regular stocking orders. Okay, Patrick, let's get started with some electrical.
Sounds good to me, Rich. Let's get started.
Shown here is a picture of the wiring diagram. Now the wiring diagram, as you can imagine, for the Spyder RT is a very large and complex document. When you receive the wiring diagram in the back of the shop manual, it'll be a very large fold-out piece of paper, but it is your ultimate tool for electrical diagnostic work. The wiring diagram is currently available on BossWeb in the preliminary shop manual information section. You could print out the document, but it would be very small on your shop computer and would be difficult to read. If you want a larger version of the document, you could take the file to a Kinko's or other printing shop and print out a wiring diagram of any size you like. But remember, the wiring diagram will be a large piece of paper in the back of the shop manual when the printed version is available. The wiring diagram is your most important tool for electrical diagnostic work. If you were going to take a trip somewhere, you certainly wouldn't go anywhere without consulting a road map. When diagnosing electrical symptoms, you always consult the wiring diagram first. Look at the diagram, study the diagram, look for the various circuits of the components in question. If you wanted to further your understanding of the Spyder RT electrical system, you would open up the wiring diagram and spend several hours studying the various circuit paths and components and their locations. What Patrick is going to do here for us in this training series is show us how to use the wiring diagram as an extensive tool. I think you will be impressed with what you can learn from the wiring diagram.
Okay, Rich, we're going to start today's training session with component location and how to read the schematic. We'll imagine we're looking at a area of the schematic, and we'll see here RDO 1-25. That would be radio connector 1, terminal number 25. To find where that connector is located, go to the bottom left of the schematic and read the small chart. Find connector RDO1 and then reference the small area location number next to it. In this example, it's number 8. Then reference number 8 in the Vehicle Location Area Callout section of the schematic. Here we'll see number 8 is located underneath the right rear. Next, we're going to reference the area next to the connector location chart, and we're going to take a look at the fuse boxes. This shows the location of the fuse boxes in the rear or master fuse block and the front fuse block known as FB. You can use these to reference the locations of the different fuses on the vehicle, and also the relay locations are located here. In addition, you'll see a series of number underneath the lower fuse block from 1 to 12 from left to right, and A to E from bottom to top on the left of the small picture. This is used to determine the terminal locations in the front fuse block. Now let's reference the area to the right of the fuse box locations, and we're going to take a look and see that these are the relay terminals and fuse block terminals as from being viewed in the fuse block, not from looking at the relay or the fuse itself. Now if you look at the illustration on the top right, you'll see that's the location of the fuse terminals in the fuse block. When referencing that illustration, you'll look to see on the left is the positive or power supply into the fuse, and on the right is the out or power supply path to the component from the fuse. Next, let's reference the illustration on the top left. This would be the terminal locations in the fuse block for a 4-pin relay. Now you'll note the numbers 85, 87, 30, and 86. These are the numbers that are on the relay, but remember you're viewing it from the fuse block, not the relay. Now you'll see there's two small circles, one on 85 and one on 86. The 85 is the positive side coming into the relay for the low current side, and the 86 is the negative side or path to ground that is controlled normally by some type of module to turn the relay low current side on. The low current side is the side of the solenoid that has the windings that when energized create a magnetic field and either open or close a switch. In this case, it closes the switch in these relays. Now it's important to note that the terminal locations circled here are not the locations that are listed in this 4-pin relay illustration. We're going to reference the load shedding relay to explain this. Note that the power supply coming into the low current side relay at position number 85 is in actuality FBD9, which if you look at the reference illustration, you'll see that the incoming current side, location 85, is at the top left. Also note that the bottom or ground path for the relay to activate the low current side would be the negative one at number 86, but in actuality it's connector FB terminal C10 in the fuse block. Just remember the terminal numbers 85, 86, 87, and 30 are not marked on the schematic. Moving on to the high current side or switched side of the relay, we'll see that number 30 is the common or incoming power side for the switched side or high current side, and number 87 is the side the current leaves the relay and goes towards the component that it is going to operate when the relay is energized. Next, let's reference the terminal locations in the fuse block for the relays. If we reference A to E from bottom to top and 1 to 12 from left to right, we could determine the accurate location of the terminals.
Patrick, it's important to remember that the illustration of the relay is there to show how the relay works. And even though it appears that D9 and C10 are directly across from each other, in actuality, on the relay, they are diagonal from each other. So if you look at the fuse block and you see C9 and D10 and C10 and D9, they're actually diagonal from each other. The reason the relay is actually wired that way is so that you could install it in either direction and it'll still work the same way. Now, this normally only applies to 4-pin relays, and we'll talk about a 5-pin relay a little later.
Well, look at that, Rich. The next slide is the 5-pin relay. And for this explanation, we're going to use the high-low headlamp relay R8. Now, a 5-pin relay can be used for 2 outputs, one in the energized position and one in the unenergized position. We'll explore that in a moment. But first, let's take a look at terminals number 85 and 86, which are still the low current side of the relay, and we can see their positions are diagonal when viewed in the fuse block. Now let's take a look at the high current side of the 5-pin relay. We'll see number 30 is the incoming power or current, but we have 2 possible outlets, number 87 and number 87A. Number 87A is used as the outlet path through the relay when the relay is not energized. On this next slide, we'll see that with the relay energized, then 87 becomes the outlet path for the current.
Okay, Pat, even though it seems like we're rambling on about relays, it's extremely important to understand the purpose of relays, how they work, how they are illustrated on the actual wiring diagram, and where the actual pin locations are in the various fuse blocks. This is absolutely critical if diagnosing components or circuit issues.
Okay, everybody, next we're going to continue on reading the rest of the schematic. We're going to begin with the top of the schematic, and on the top of the schematic is where you'll see the circuitry for the CAN high and CAN low communication wires. The CAN, Controller Area Network Protocol, is an ISO International Standards Organization standard for serial data communication. The protocol, computer language, was developed for use in automotive applications. The CAN bus links several ECUs and sensors in the vehicle's electrical system. 2 wires connect each component, and they are in constant communication with each other at a rate of about every 25 milliseconds. The white-black wires are referred to CAN low, and the white-beige wires are referred to as CAN high. In addition, the CAN wires also provide communication with buds when connected through the diagnostic connector. Consider, if you will, the CAN wires as a telephone line where the modules are constantly talking with each other really fast so they can all stay updated on the latest information and take action as necessary. The CAN bus system integrates several electronic control units into one communication loop. The units in communication are as follows: the radio, the REC or multi-function switch left, the cluster, the WPM, windshield and park brake module, the ECM, the DPS or dynamic power steering, the SAS or steering angle sensor, the VCM, vehicle control module, also known as the VSS for vehicle stability system, the TCM or transmission control module, if so equipped, and the YRS or yaw rate sensor are all in the CAN loop. Now if we look at the upper right corner of the schematic, we'll see a small area that lists the switches in the left multifunction switch that use CAN communication. Remember, these switches can only be tested with buds. In addition, the signals from the cruise switch located on the right multifunction switch are sent to the left multifunction switch, and those signals are also converted to CAN.
Okay, Pat, let's make it clear that the cruise control switch in the right-hand multifunction switch are normal contact switches, and they can be tested with a multimeter at normal wire and connector locations as identified by the wiring diagram. Once these connections are made at the multifunction switch on the left, they are converted to CAN inside that module. Now, moving down the wiring diagram, the next thing we see are the high amperage fuses. These are the fuses that are located in the back of the vehicle, and there are the very high amperage or the large square fuses. They are all connected to a large bus bar which is directly connected to the battery. They feed the main power to the main fuse assembly, the lights fuse, TCM solenoids, DPS motor, VCM valves, and the VCM pump, and also the main accessory fuse. Next, down the wiring diagram, you'll see the lower current fuses, which are the fusers that are in the front fuse block. There are several accessories and various components that are operated with these fuses, and the fuse locations and wire terminal connections can actually be identified from this wiring diagram. For example, take a look at the accessory plugs fuse way over to the right of the screen. It's a 10 amp fuse. We can see that fuse is in location F9 or fuse location 9. It's a 10 amp fuse, and its terminal connections are actually FB B9 and FB B8. Even further down in the wiring diagram, we see the next row, or the relay section. Here you can see the main relays, the cooling fan relay, the headlamp relay, and the load shedding relay, which Patrick will talk about a little bit later.
Rich, I'd like to talk about the next portion a little bit further down the schematic, because this area can be a little bit confusing for some of the technicians I've seen in the field. What you'll see is some of the components are split up into different segments. I'm going to use this example as the cluster. The multifunction gauge or cluster is split up into several areas across the schematic. Here you'll see that the multifunction gauge is actually split into 6 separate segments across the schematic. Now, depending on the component, sometimes, as in this case, you'll see a curvy line at the sides of the instrument cluster as it's split up. But in some cases, it'll just say 1/2, 2/3, etc., indicating there would be 1 of 2, 2 of 3, 3 of 4, 4 of 5, etc. That's just something to be aware of as you're looking for different pieces of components across the entire schematic. I want to come back to the schematic and just kind of summarize the different areas that are located on the schematic that you may be concerned about. The very top of the schematic shows the CAN routing. Right beneath that would be the area that would show your 12 volt positive supply side of the system. And that would be the supply from the battery to the various components. Now in the center of the schematic would be the location of the main components, things like the ECM, the radio, the CB, and various other components in the RT system. Now located at the bottom of the schematic is somewhat overlooked by a lot of technicians is the 12 volt ground path from the components back to the negative side of the battery, or the ground, kind of commonly considered the ground of the system. Now all the way at the bottom of the schematic is, as we discussed before, the connector locations, terminal locations, and locations for the fuse block and relays, things like that. Now we want to discuss power distribution. What is the sequence of events that happens to get all the modules on the RT vehicle to power up when the ignition key is turned on? Now you'll see that power is supplied from the battery at all times to both main relay 1 and main relay 2, and also the ignition switch. At both main relay 1 and main relay 2, there's power at all times to the low current side of the relays, and also the high current side of both relays. And you'll notice at the ignition switch there's power at hot at all times located at 2 locations at the ignition switch. Now what turns on main relay number 1 and main relay number 2 is the ECM, or engine control module. That's actually what activates the ground side of both relays. When the ignition switch is turned on, current flows through the ignition switch and then enters the ECM at terminal A2. This activates the ECM. And once the ECM has been activated, the ECM can then send a ground signal from terminal H2 of the ECM to each the relay, both main relay number 1 and main relay number 2. At that point, both relays are now activated. And with the relay activated, the contacts now close. Then the power can distribute to the necessary modules through main relay 1 and main relay 2. Now we're going to talk about power distribution to something called the non-critical loads. Non-critical loads would be the hood actuator, front compartment light, front and rear heated grips, and the air-controlled suspension on the RTS model. Now, power through the power distribution to the non-critical loads comes through something called the load shedding relay. Now, it's called the load shedding relay just in case the battery voltage drops below 11.8 volts. It'll shed the non-critical loads. So that relay would be turned off, and then the power to the non-critical loads would be shut off. Now the load shedding relay is supplied to ground not by the ECM but by the instrument cluster, which is a module itself. Now that ground from the cluster is supplied from terminal CL number 19 at the back of the instrument cluster. As long as the system voltage is over 11.8 volts, the instrument cluster will supply the ground to the load shedding relay. That will activate the relay. Now once the relay has been activated, the contacts will close inside of that relay, and then power can be supplied to all the non-critical loads in the vehicle. Okay, moving along now, let's talk about the windshield park brake module, or WPM. Okay, this module is located in the upper console, right in the center, underneath of the windshield. It contains the mechanism to operate the windshield, as well as the module and the motor for the windshield. In addition to operating the windshield, it also is the module that operates the motor for engaging and disengaging the parking brake. Okay, now let's take a look at the basic operation of the electrical portion of the windshield park brake module. Let's start by talking about what components are involved in the windshield park brake system. First, there's the WPM module. There is the parking brake switch located on the center console. There is the windshield up-down located in the left-hand rec or left-hand multi-function switch. In addition, there's the windshield motor, which is located on the WPM module. Also included is the parking brake motor. And finally, we have the parking brake switch, which is located on the front bell crank for the parking brake actuator. Okay, now for operation, the first thing is power is supplied to the WPM module from main relay number 2 to terminal number 5 of the WPM once the electrical system has been activated. Next, the ground comes in at terminal number 7 at the WPM. Alright, first we're going to cover operation of the windshield. The signal is sent from the left-hand multifunction switch to the WPM when either the up or down windshield is selected. Now, it's important to note that this switch is a CAN signal. So it's converted to CAN since the left multifunction switch is a module. And as we stated before, it can only be tested with buds. And that signal comes in at terminals 6 and number 8 at the WPM, which are the CAN high and CAN low communication wires. Now, once the module gets the signal from the switch for either up or down, it will send voltage to the windshield motor to either raise or lower the windshield. Depending on which direction the motor needs to be driven, the module can reverse the polarity to the motor. Positive applied on one side, ground on the other side of the motor will send it in one direction. And when that polarity is reversed and positive is on the other side and negative is on the opposite side, it will send the motor in the other direction. Okay, let's talk about the operation of the parking brake now. When the park brake switch is in the off position, current is supplied from terminal 10 of the WPM to terminal 12 of the WPM through the park brake switch located on the center switch panel. When that signal is received at terminal 12, the WPM then determines to send current to the parking brake motor. When the parking brake is fully released, a protrusion on the front pulley contacts a small contact switch. The contact switch opens the circuit from ground to the WPM terminal number 3. The module then knows that the parking brake has been fully released and shuts off the voltage to the motor. To apply the brake, the parking brake switch is pushed to the on position. At this time, current is sent from terminal 10 through the switch to terminal number 1 of the WPM. At that time, the WPM then sends current to the parking brake motor in the reverse polarity as application to apply the brake. Now, as the brake is being applied, when it gets to the end of the travel, the amperage output of the WPM to the parking brake motor increases as the brake tightens. The WPM is calibrated to stop applying current to the motor when that amperage value exceeds a certain threshold. You'll note that the parking brake pulley in the front rotates forward, pulling on the brake cable. At the same time, the protrusion is moved away from the micro switch contact. When the protrusion moves away from the micro switch, a ground is then supplied through that switch to the WPM module. When that ground is applied, the WPM is calibrated to determine that the parking brake is in the applied position. and begins to look for the threshold amperage to stop the current flow to the motor. Additionally, the ground through the switch also directs that ground signal to terminal number 17 of the multifunction gauge, and the multifunction gauge knows that the brake is in the applied position. If there is no ground signal to terminal number 17 at the cluster, and the electrical system is shut down by the ignition switch being turned off, the backup warning alarm will sound. The ignition switch will need to be turned back on, and then the parking brake applied before the ignition is turned off again. Some additional information here is that each time the electrical system is powered up and the parking brake is tried to be released by activating the switch, the WPM module will try to apply the brake first, so it'll take 2 clicks, 2 pushes of the switch to release the brake each time the electrical system is powered up. After that, during the cycle, it will only take 1 push to either engage or disengage the brake switch.
Okay, Pat, thanks for that explanation of the WPM. Before we move on to the engine management system, I'd like to remind everyone how important the wiring diagram really is. Not only is it your number one tool for doing diagnostic work on any vehicle, it's also your number one training tool. Good technicians will look at a wiring diagram and train themselves and help them understand how things work. If you want to know how a WPM works or one of the many components on the vehicle, simply look at the wiring diagram, and when you understand the wiring diagram and you understand what Patrick is telling us here, you'll be able to easily understand how that component or how that circuit works. Our newer wiring diagrams show actually the inside of various sensors and inside of components, so you can see what's going on inside that component, and good technicians can understand exactly how a system works simply by looking at the wiring diagram. So again, it's very, very important to understand what the components are, where they are, and how to read the wiring diagram. If you want to get the most from this training, I suggest that you get the wiring diagram out, spread it out on the table, and listen to the webcast. And remember, you can listen to this webcast as many times as you like. Simply use your pause button on the webcast and listen to what's being explained while looking at the wiring diagram and following the various circuits. You'll quickly understand how easy it is to read the wiring diagram and understand how a system works. Okay, let's continue on. The engine management system is basically the same as the Spyder GS or RS models. The only thing that we're going to talk about in this training material is the differences on the Spyder RT. The first thing we'll notice is that the engine control module or ECM is different on the RT. It's a new component. Since it has different wiring connector blocks, we'll need a new tool for doing pinouts and testing of the wiring harness coming to and from the ECM. The new tool that we have is part number 529-036-166, and you can see it here. Some of you may have a tool that looks very similar to this, as we introduced it to ATV and then showed you or talked about modifying it for C2IS models. So if you have this tool, you're all set. But it would be best to order the new tool that's pre-modified. Also, you'll notice that the RT has 2 heated oxygen sensors. These can be seen on the wiring diagram by HO2S1 and HO2S2. Having 2 oxygen sensors rather than 1 like on GS and RS models allows us to have a more finely tuned calibration and more carefully monitored output. You'll notice inside the heated oxygen sensors there's a heating element. This heating element allows the oxygen sensor to produce its reference voltage sooner after the engine starts. The reference voltage that is produced is actually comparing the amount of oxygen in the exhaust gas. A voltage of 0.1 to 0.9 volts is what is measured. Between 0.45 and 0.9 volts would indicate a rich condition, and from 0.1 to 0.45 volts would be a lean condition. By monitoring this voltage, the ECM can adjust the engine mixture accordingly for optimal performance and minimum emissions. For more information on oxygen sensor operation and theory, as well as the combustion process, refer to the BRP Guide to Service Fundamentals textbook, part number 484, 800, 168. Okay, Patrick, what's next?
Another thing that's unique about the RT engine is that it has two NOx sensors, piezoelectric NOx sensors, one located on each cylinder. Each of these sensors contains a piezoelectric crystal. That crystal will generate small amounts of electricity when it is vibrated. Now obviously it vibrates the entire time the engine is running, so it's always producing electricity. However, the ECM is programmed to detect the frequency of detonation. So if for some reason somebody used a lower octane fuel that they should, or they had some degraded fuel, and the engine were to have a detonation situation, the NOx sensor would detect that frequency of detonation, compensate by increasing the amount of fuel into each individual cylinder, and compensate and keep adding that fuel until the detonation were to cease. This brings us to why it's so important that the recommended fuel octane of 91 octane is used in the RT vehicle. If 87 is used, the NOx sensors will both detect detonation in the individual cylinders and increase the amount of fuel to the cylinders. It won't hurt the engine, but you will consume more fuel than you should be using. So make sure that you use the correct octane fuel, or recommend to your customers to use the correct octane fuel. Something totally new on the RT platform introduced this year is the ETC, or electronic throttle control. The ETC eliminates the need for a throttle cable from the twist grip down to the throttle body. There's one actuator and one sensor incorporated into the system. The TAS, or throttle accelerator sensor, replaces the cable-operated twist grip. The ETA, or electric throttle actuator, is the actuator that actually moves the throttle plate at the throttle body. The throttle actuator sensor incorporates a dual output Hall effect sensor. It puts out two linear voltages. One is used for redundancy in case one were to not be recognized. The linear signals generated by the dual output Hall effect switch are sent to the ECM. The ECM in turn interprets the signals as a position of the twist grip, and in turn sends electrical signal to the electric throttle actuator. It can then accurately control the throttle plates in the throttle body. One important thing to remember about the electric throttle actuator is to never put a voltage signal directly to the actuator. It will permanently damage the actuator. Complete diagnostics are outlined in the shop manual. By incorporating ETC into the system, it was easy to add an electronic cruise control function to the RT platform. Another item that's new in the EMS system is the TPS, or throttle position sensor. Instead of being a single linear voltage dividing circuit, you'll notice it incorporates two. And again, it has two separate sensors inside of one sensor, just for redundancy purposes in case one signal is not recognized. Okay, what I'd like to do right now is talk about the differences in the vehicle stability system. There's only really one big difference, besides some very minor calibration changes to take a look at, and that would be that now there's only 3 wheel speed sensors incorporated. Before there was 2 in the rear on the RS and GS models. There was 2 rear wheel speed sensors. However, now there's only 3 sensors. There's 1 per wheel, so it's going to be quite noticeable when you see it in the shop. Yeah, I want to talk about the central panel switches and a little bit about the central panel switch illumination. Now, I've just picked out the fog light switch, and I want to talk a little bit about that. First thing I want you to take a look at is around the outside of the switch. You'll see there's a dotted line. Now, anytime you see a dotted line around a component in the schematic, that means it's an accessory. So the vehicle may or may not have that particular component. It could be in the case of a TCM, for example, may have a dotted line. In this case, the fog light switch has a dotted line. Now, I also want you to look inside of the switch, and you'll look to the very left of the switch diagram, and you'll see a small bulb. That is the illumination bulb for the switch, and it is powered, in this case, from one of the relays, and it's fog light, so that means it would be the load shedding relay would power this switch and the light. I'd also like you to take a look down at the bottom on the negative or ground side wire that's going to the ground, and you're going to see a resistor in line. Now, that's an 8.25 k ohm resistor, which is approximately 8,250 ohms of resistance that's been added to the negative or ground side. Not only the fog light switch, but each of the central panel switches has this resistor incorporated into the wiring harness going to the ground. Now, what it does is it increases the resistance in the circuit, thus decreasing the amperage flowing through the entire circuit, including the bulb. By doing that, it reduces the intensity of the bulb. If it did not reduce the intensity, it would be too bright, and that could be distracting to the operator of the vehicle. Let's talk about the hood actuator front storage compartment light. Available as an option on some models, but standard on the RTS model is the hood actuator and the front storage compartment LED light. The vehicle's already wired for the hood actuator and the light. The only thing that would have to be installed would be the light, the hood actuator, and the hood or front case opening switch, as it's called, for the front storage compartment. Power is fed to the central panel switch via the load shedding relay, so the ignition switch has to be in the on position for the hood actuator to operate. Additionally, power is also supplied through the load shedding relay to the LED or top case LED, which is really the front storage compartment light. Now, the front case opening switch, or front storage compartment switch if you would, supplies a ground. It's a 2-position switch, and depending on the position of the switch, whether the hood is open or closed, is going to determine in which direction the ground would be diverted. Now, if the hood is open, the ground path through the switch would go to the LED light, and the light will illuminate as long as the ignition switch is in the on position. And when the hood is closed, the switch is in a position that will supply the ground to the hood actuator. Now, the hood actuator won't actuate until you actually push the hood actuator button, and then power is sent through the switch in the central panel to the hood actuator, and then the hood would actuate and open up.
Wow, that's a lot of information, Patrick. I think we ought to stop here.
Well, Rich, this was the condensed version. Wait till part 4. There's going to be a lot more information in that one, too.
That's right, and we're really looking forward to that one. Patrick, remember that the wiring diagram is not only an essential tool for proper vehicle diagnostic, it's also an extremely valuable training tool. A lot can be learned by just studying the wiring diagram. Wouldn't you agree?
Absolutely, Rich. You know, the best technicians out there would never even attempt to try to tackle a vehicle electrical issue without first studying the circuit in the wiring diagram.
That will conclude this Can-Am Roadster Spyder RT Technical Training Series Part 3. Remember to go on to BRPTI and take the short exam verifying you viewing this training session. Also remember that Part 4, Electrical Systems 2, will be first aired on December 2nd. Thank you for attending, and we'll meet you again next time.